Hello. In this lab, we are going to observe the motion of an object being dropped by rest and falling straight down. This experiment will measure the object's position with respect to time using three cases: an observed measure position from the tracker app, and two Glowscript model predictions based on Newton's second law. The reason Newton's second law is used is because it states that acceleration is directly proportional to net force. It can then be written as this equation, which is F net equals change in momentum over change in time. This can be derived to this velocity equation, then to this displacement equation, connected by the fact that V average equals Vf plus Vi over 2 for constant forces. But if it's non-constant, V average just equals V final. For both models, V average is just going to equal V final, just for the sake of simplicity. Now, the second model applies drag force. Drag force acts upon any object moving in a fluid, in this case that is air, and it always does so in opposition to the object's motion. This drag force is directly proportional to the square of the object's velocity. The turbulent drag force can be calculated by this formula, which I reduced to this, and this coefficient is 0.002 for the second model. For the first model, where the drag force is excluded, this b is equal to 0. The lab is set up using a mass of 0.058 kilograms, and the reference length being 0.068 meters. These are the initial positions and times, and the first recorded ones, just to give an example, and to show that the time intervals are 0.041, and so the position and velocity values are calculated iteratively. So these models aren't going to be entirely correlative to that of the observed data which the tracker app got, and these are a result of a variety of factors. To name a few, tracker's location marker is not always consistent with pinpointing the center of the object at a given time, and the exact value of air density and room temperature of the test area are unverifiable, along with other values pertinent to B. Most of the things I used to calculate B were based off of approximations. For example, the diameter was converted to the radius, and the radius was used to find the reference length, which is within this equation. And so here is what the tracker app got. It took the footage of me dropping the ball, and it got this data from it. I have these two models which show the ball falling with gravity just acting upon it, and with the gravity and the drag force acting upon it. Here is the data represented in the graph. And you can see that Model 2 barely is better than Model 1 in being more accurate to the observed data. This is most likely because Model 2 took into account another factor than Model 1 did. And here are the graph of the velocities of the two models. Model 1's velocity stayed at a constant slope, meaning a constant acceleration. However, Model 2's starts to deviate, and that's because eventually Model 2 has a terminal velocity, and that is when the drag force equals the magnitude of the gravity, and so the F net becomes 0, and the ball is then moving at a constant velocity, because Newton's first law states that if any object is at an F net of 0, that means it's either at a constant velocity or it's at rest. Now, in the case of the ball being thrown downward instead of simply being dropped from rest, it can be seen that the terminal velocity is still the same, because in this case, with the ball being at rest, the terminal velocity is negative 16.8. And in the case where the velocity is the initial velocity is negative 5 meters per second, the terminal velocity is still negative 16.8. And that's it. Thank you.